All right. So for today, we get to go backward in time a little bit, and we're going to go back to doing some limits. And there's a reason that we're doing it. In 4.5, we get to talk about some limits that we could have done this early on in the year, that sine x over x, and there is a way to do it and to think about it geometrically. We glossed through it. So we will knock that out today. But in 4.5, we're going to be talking about two big ideas. We're going to be talking, I guess it's really one big idea. The first is indeterminate forms. Indeterminate forms. And there's a goofy name that we're going to get to hear here. And there's a variety of different ways you see this spelled. French mathematician L'Hopital. So it looks crazy. L'Hopital. Okay, our focus today is this idea of indeterminate forms and what we will call L'Hopital's rule. So some books, you'll see this as hospital, looks like La Hospital, but it's the same name, just pronounced and changed a little bit. So indeterminate forms are the first kind of piece here that are awesome. And there's some wonky stuff that happens. You guys know a few things already, and you have some intuition for some of these. What's a number you can't divide by? 0. So like if I did 1 over 0, it's undefined, right? So there's a natural kind of question, though. 1 over 0, it's broken. Whatever, that's fine. 2 over 0 is broken. Any number over 0 is broken, with maybe one exception. And there's this weird little situation where we get ideas and things that are super counterintuitive, and this is one of them. If I were to take 0 divided by 0, you have really two different ways that you might think about this where you're at right now. It's either 1, because anything over itself is 1, right? But that doesn't feel right to me. Or it's undefined, because anything divided by 0 is broken. Like one of those two are the natural kind of thought that you might have. Turns out that neither of those are really correct. Now, two of the indeterminate forms that we're going to see today, one of them is 0 over 0, and we can deal with this. But the other one is infinity over infinity. Now, we're going to say our first section today is 0 over 0 and infinity over infinity as indeterminate forms. Now, what's unique about these, and it's just something that you've never dealt with in here, is as we look at these functions, or any function that we think about doing this, we're not saying it's undefined anymore. All we're saying is that it's indeterminate, and that's a weird idea. It depends on what the context is. There are situations where 0 over 0 is undefined, but there's also situations where 0 over 0 is 1 or 2 or 3, and we just don't know until we actually see that specific problem. The same thing happens here, and it feels really odd to think this, but infinity over infinity, anybody else's gut say it should be 1? My gut does, but it's weird because infinity is not really a number, right? We're taking something infinitely large over infinitely large, and maybe they're the same size, maybe it's 1, but maybe they're not, and that's a weird idea. There are infinitely many different sizes of infinity, which is a strange idea just on its own, but these are not straight undefined. These are indeterminate, and we're going to be able to deal with these. So let's jump back in time here real quick, and we're going to evaluate a limit. So let's evaluate the following. So here we go, evaluate, and let's just try it. I want us to take the limit as x approaches 2 of x squared minus 4 over x minus 2. Okay, as we look at these, we have to think all the way back to the beginning of the year. If we're trying to evaluate out a limit, does anybody recall the very first thing that we checked for? Direct sub. So if we tried it, we would get 2 squared is 4 minus 4 is 0 over 2 minus 2 is 0. We get 0 over 0, right? Now, that is a failure right off the bat. It just doesn't work. Do we have a way to algebra to fix this? What is the algebra fix to this? Let's factor. What do you want me to rewrite then? So we can factor this numerator as a difference of two squares. So we'll just say some algebra happens, and here we go. The limit as x approaches 2 of x squared minus 4. Just kidding. How does this factor? X plus 2 and x minus 2 all over x minus 2. And we wind up seeing that those fall out, and then we just tried direct sub again. And all of a sudden, we had the 0 over 0 situation that is not undefined. It was just indeterminate at that point in time. What is this actual limit then? It's 4. And we see that in this situation, and this is a weird idea, but what we just witnessed was a situation where 0 over 0 was equal to 4. Like, that's what just happened. And it's strange that that does happen, but we've been dealing with this indeterminate form from the early on point of the year. We just never really thought about it in this much detail. Okay, we can evaluate it, and it just depends on the particular function. What if we try a slightly different one, and I just want to try one more. So we had this first one, 0 over 0 became 4. Weird idea, but we can run with it. Okay, I want you guys to try one more limit, and we might have to work this one together. We'll see. I want us to also take the limit as x approaches infinity of 3x minus 2 over x plus 5. And it's been a while since we've done limits, so you're naturally going to be a bit rusty. If we direct sub here, what's 3 times infinity? Minus 2. Let me rephrase. What's your gut say that is? Because that's a weird idea. If you have something infinitely large and you subtract 2, what is it now? It's still infinity. That seems reasonable to me. So this is still infinity up top. Okay, fine and dandy. Over, what's infinity plus 5? It's infinity. So we get an infinity over infinity situation. And it's weird. We can't say it's really a number. It's what we call indeterminate. And we do have some tricks to get through to this one. I'm going to ask you guys to dig deep. I'm going to give you like 60 seconds working with one another. How do we fix this with algebra so that we can do it? Cool. Play around with it. I'll give you like 60 seconds. Don't be afraid of being wrong, right? Like being wrong is part of the game. Cool. Talk it out. Try things. This one little change in algebra. If I direct sub now, I get 3 minus 2 over infinity, and no longer am I indeterminate. What's 2 over an arbitrarily large number? 0, right? Yeah, like it seems weird to just say it's 0, but it is. 2 over infinity is 0. So I get 3 minus 0 over 1 plus 0, and we do in fact see that this limit is 3. So just like we saw a moment ago, we have these really wonky forms. 0 over 0 was actually equal to 4 in this situation, and infinity over infinity was actually equal to 3 in this situation. They're going to change. It's going to be entirely dependent on the problem. Now, both of these limits that we just calculated out, we haven't had to do a limit in like 5 months, but both of these limits we could do completely algebraically. We didn't have to use this idea of L'Hopital yet, but it turns out that maybe if we stand on the shoulders of giants in the world of math, make stuff a lot easier for us because people have already done the hard work for this. So looking at these, this is just a nice demonstration of, hey, these forms do show up and they're wonky. Let's keep kicking with it. When we direct sub with a limit, and we will get limits again, just so you guys know, it's been a while. We're not going to have to do a ton of them again, but we are going to learn today an easier way to do all the limits that we had to do earlier this year. So they're pretty convenient because we get to take a shortcut through them. So when we're looking at this, we have a bunch of indeterminate forms, and we're just going to go ahead and list. There's only a couple of them that show up on the AP exam, and I'll highlight which ones those are. Indeterminate forms. But it is nice to see that, hey, there's a bunch of different things that wind up being wonky that are indeterminate, not undefined, but indeterminate. Okay, so the first two that we've already seen, they show up all over the place, and we've already looked at them. I'm just going to include them again. 0 divided by 0 and infinity divided by infinity. These two right here are on the AP exam. Now, when I'm going through this, just as a reminder, just because it's not on the AP exam doesn't mean the other stuff that we're going to see doesn't matter. It just means you're not going to see it on this one specific test. If you go on to take Calc 2, 100% you will see these things in Calc 2 and Calc 3 and so forth and so on. Okay, but there are some other wonky ones that my gut doesn't sit super comfortably with. If I take 0 times anything, what should it be? You would think it'd be 0, right? Well, maybe not. 0 times infinity is not 0. It's indeterminate. It could be 0, but it could be 5 or 1 or 3 or it doesn't matter. Any of those indeterminates. Okay, these ones are not going to be on your exam, but they are worth knowing and knowing that they exist. Infinity minus infinity. My gut says it should be 0, but when we consider a bunch of different types of infinity, maybe it's reasonable that it's not always exactly 0. Cool. This one's wonky. 0 to the power of 0. It's not 1. Not going to be 1 in that situation. You can ask your calculator if it's 1, and it will just tell you. I don't even know what it says. I'm going to try it real quick. 0 to the 0. Yep, my calculator says domain error, which is just it saying, I don't know what it is, because it's indeterminate. It needs a context to be able to work with it. A couple more that are weird. 1 to the infinity. It's not 1. I mean, it could be 1, but it's not guaranteed to be 1. And one more that we're going to see here, infinity to the infinity. All of these forms of numbers, they're wonky, they're indeterminate. They could be a variety of different things, just depending on the problem. Now, what we hope for when evaluating a limit is we want it to be indeterminate. If it's a hard limit that we can't work out using direct sub and stuff, we want something indeterminate because we're going to have a way to sort them out. That limit is weird. Right here, that sine x over x, and we'll knock this one out here in just a moment. It's the one from earlier in the year. If I tried to do this limit as x approaches 0, sine x over x, do you guys remember what this is? What is it, Leanne? It's 1. Now, if we just tried direct sub, though, we get sine of 0, which is 0 over 0. It's indeterminate, right? It's at 0 over 0 form. There's not a nice way to think about that, but it is one of these. So, as we're going through, the big goal is we want to determine if it is indeed an indeterminate form. So a couple examples just to kind of get us a feel for them, and we will take a brain break here in a few minutes, just so you're aware. But I want example, and I just want to know which, if any, which indeterminate form. All right. So we have like 4 of these that I want you guys to play around with. And the first of these will say, I'm not going to write it as a limit. I'm just going to say, here's the x value that we're checking for it to be indeterminate at. So that's a little bit nicer. The first of these is if we take the sine of x plus 1 over x plus 1. And if I try to evaluate this or take the limit, however we want to interpret it, at -1, I want to know which indeterminate form do we get. Now, I'm going to use a little bit of editing magic. I don't think you need to hear me read all of them out. I'm going to keep my indeterminate forms up on the board. While I'm writing the next 3, I want you guys to discuss this one and tell me which of these, if any of them, does this fall into. So I'll give you a minute, and I'm going to use a little editing stuff. And all right, so checking these out, I'm going to try to blast through here. I don't know, are answers orange or yellow? Okay, deal. So when we plug in here at -1, we get the sine of 0, which is 0. So this is a 0 over 0, right? Indeterminate, easy. This one, we get e to the 0, which is 1 minus 1 over the sine of 0. That's a 0 over 0 situation again. Okay, this one is the wonky one. We have to do natural log of x over 1 over x. But if we do this, we wind up seeing that as I get really close to 0, this one goes to infinity. And really it goes to -infinity is what happens. Am I taking that one too briefly? Like anybody look at that and go like, what the hell do you mean it goes to -infinity? Yep, so that's fair. Let me draw this correctly. If we look at the natural log, this is what its graph looks like. And as I get really close to 0, I shoot toward -infinity. So that's what I'm using to make that sense of that. So I get -infinity over infinity, and that's an indeterminate form. What about this last one? That'd be 1 minus 1 is 0 over, what's cosine of 1? 1. Is that indeterminate? No. And that's okay that it's not indeterminate. This is an easier limit. This would just be 0. Nothing crazy has to happen with it. And the natural part or place that people get goofed up with, once we learn L'Hopital's rule, which we're about to, is people will try to use this to work out every single limit, but it is imperative that we can get to one of these forms before we use L'Hopital, which we'll see in just a second. Okay, what do we want as a brain break? Should we just get some of the cards, the first 8 cards that we have? Okay, I'm cool with that. Gosh, my cold is pretty much gone, but I was complaining it's turned into a sinus infection. What I do think, though, is that we're at a place where we can really talk about L'Hopital's rule. So that's pretty cool. So let's do that. Okay, so 4 here, and I don't know, like if we go category 2, it's way above my pay grade also, so I'm not sure. But we get a theorem, and we are going to actually define for ourselves L'Hopital's rule. And I don't know if this is how your book spells his name or not. El Hospital is what it makes me think of a lot of the time. L'Hopital. Yep, this is how they spell it. So here we go. For L'Hopital's rule, it's when we're trying to evaluate limits is what we're going to use this for. So if we let f and g, so let or given, but let is easier, let f and g be differentiable, and I'm just going to call that diffable, on an interval containing some number c. Now, it doesn't even have to actually be differentiable at c. We just need the c value in here. If we have f and g are differentiable in that interval, and we get the following, that g prime of x is not 0, then we get the following lovely relationship. If I try to evaluate, and here's our big if statement now. If you give me f of x over g of x, and it is equal to one of those ugly, or the nice rather, indeterminate forms, 0 over 0, or infinity over infinity, whenever x is c, so we'll just say at x equals c, then it turns out, if you give me this and I try to evaluate it and it gives me one of those two forms, there is a really easy trick that we can do. If we want to evaluate this function, we'll just say if the limit as x approaches c of f prime over g prime. So notice all we've done is we've taken the derivative of the top and the bottom. Really important here, another place people get goofed up. We did not quotient rule. I just took the derivative of the top and the derivative of the bottom. No quotient rule, just do the derivative. If we get the derivative here and then take the limit and it winds up being some number L, well, then it turns out that the actual limit of f over g without the derivatives is also going to be equal to L. And this makes really, really nice limits out of some awful things. If you want, and not if you want, I probably will show you anyway, we'll go back and I'll show you the geometric interpretation of this limit that we talked about earlier in the year. But let's take a look at this limit right now. So we're going to use L'Hopital's rule. If we get an indeterminate form and we don't know how to fix it algebraically, or if we don't want to fix it algebraically, we can simply just do the derivatives. So let's try them out. So examples, let's get a few of them. So on our first one, we're going to try to evaluate the limit as x approaches 0 of sine x over x. Now, we still are going to commit to starting these problems the same way. What's the first thing that we should try? Direct substitution. And the sign of 0 would be here, and that's 0 over 0. So right off the bat, when we try direct sub, and I'm going to switch to orange for these, we see that this thing becomes 0 over 0. which is kind of a bummer before. The good news is that it's not a bummer anymore. This is exactly what we want to see. Is this one of these two indeterminate forms? Yeah, so all we have to do then to evaluate this limit is we just need to take the derivative of the top and the derivative of the bottom. What is the derivative of sine x? So I'm just going to say let's hop on to our next step, and right, and then we'll just check it out. The limit as x approaches 0, and I've heard one person say it quietly, but my hope is that everybody can. What's the derivative of sine? So here's the cosine of x over what's the derivative of x? 1. Now let's try this direct sub. What's cosine of 0? 1 over 1 equals 1. Therefore, this limit, and we would have to actually say this, and this is the tedious part of it. Therefore, the limit as x approaches 0, since we just did a completely different limit, we need to be very clear with it, of sine x over x equals 1. And we have an easy way to evaluate some really nasty seeming limits. Okay, let's see if we can't find another one. And let's do a couple more here. I don't think I'm going to give you homework this evening, but we are just going to work problems for the next 7 minutes then. Cool. All right. On B, let's check them out. I want the limit as x approaches 0 of the tangent of x over 6x. And I'm going to give us one more, and I want you guys to try a couple on your own here. You'll do this one. I'm going to put B and C up here. I want you guys to talk through them with one another, and we'll come back together either with a couple minutes left in class or at the start of class tomorrow